The next property is also the same as before. So this is conjugate symmetry, conjugation and conjugate symmetry. So this says that if you have a single xn that has Fourier transform capital X, then the complex conjugate of this time domain signal will have a Fourier transform that is a complex conjugate of this spectrum with a frequency reverse here. Okay? So if your signal xn is real, which means that xn is equal to xn complex conjugate, then this means that the spectrum should be equal to this, which means that it is conjugate symmetric. Okay? So this means that it's conjugate symmetric. Okay. So because of this conjugate symmetry, as in the continuous time case, we can show that the real part of the spectrum is even, the imaginary part is odd, and similarly for the magnitude and phase. And you can show that the even part of this signal has a Fourier transform that is equal to the real part of the spectrum of x, and the odd part is equal to the imaginary part of the spectrum. Okay. And then this differencing is analogous to differentiation. Okay. So this is actually quite straightforward, right? Differencing in the time domain is xn minus 1. So xn has a Fourier transform that is capital X. Xn minus 1 is basically a time shift. So it would be the spectrum times a phase shift. Okay? All right, and then we have the accumulation, which is analogous to the integration in the continuous time case. Okay, so what would be the Fourier transform of this accumulation? Right. Now we know from the differencing property that if you take, okay, so by differencing property, okay, if you take yn minus 1, okay, from the above equation, we know that this will give you xn. Okay. But by the differencing property, we know that the Fourier transform of the left-hand side should be 1 minus e to the minus j omega y of e to the j omega. And on the right-hand side, this is just the Fourier transform of x. Okay. So by this fact, you would expect that, if omega is not 0 or some integer multiple of 2 pi, then you would expect that y should be equal to x divided by 1 minus e to the minus j omega. Okay? So we expect y e to the j omega equal to something like this. Okay? For omega that is not equal to 0 plus or minus 2 pi, or so on and so forth. Okay? Because if omega is 0 or plus or minus an integer multiple of 2 pi, then this would become 1, and the denominator would be 0, right? You would not be able to divide this 0 to the other side. Okay? But for omega that is not integer multiple of 2 pi, you expect that the accumulation should give you a spectrum that looks something like this. Okay? And indeed, that is the case. Right? Indeed, that is the case for omega not equal to 0. But for omega equal to 0, we need an additional term, right? Recall that this is similar to the integral in the continuous time case, right? So when omega is 0, we need an additional term to account for the DC or average value of this signal, okay? So this accounts for the DC or average value of the accumulation. Okay. Right. Now, a typical example of a signal obtained from accumulation is this unit step function. Okay? Because for a unit step function, you can view it as a accumulation of, delta functions. Okay. So let's first define the function g as this delta function. And a delta function has a Fourier transform that is just 1. Okay? Okay. Now we know that xn, which is un, can be viewed as the accumulation of this delta function, summing m from minus infinity up to n. Okay? So when n is less than 0, then this summation is 0. But whenever n goes, greater or equal to 0, you will be summing up this delta function at time 0, and therefore the outcome will become 1. Okay? So this summation will give you something that behaves exactly the same as this unit step function. Okay. Now the delta function, as given above, is defined as this function g. Okay, so let me replace it with g. All right. Okay, so by the above formula, right, what we have here in the time domain is this should be summed up to n. Okay, so what we have here in the time domain is an accumulation of the function g. Okay, so the Fourier transform by applying the above formula should be 1 over 1 minus e to the minus j omega g e to the j omega plus pi g e to the j 0 summation delta omega minus 2 pi k. Okay, from minus infinity to infinity. Okay. Now g is a constant 1 for all omega. So this becomes 1 over 1 minus e to the minus j omega plus plus pi times the sequence of delta functions. Okay. Okay. So all of these are, more or less the same as in the continuous time case. Okay, so I could have, I would have wanted to skip all these, but anyway, it's a good practice to do. Okay. Right. So then similarly, we also have this, time reversal, right, where, we're with, yn equal to x of minus n, then what would be the Fourier transform of this? Okay. So, by the definition of Fourier transform, right, this is just the summation of yn times e to the minus j omega n. I replace yn with x of minus n. And then I can do a change of variable. Okay. So suppose I let m equal to minus n, okay? And I can write this as summation xm, m also going from minus infinity to infinity, e to the minus j, okay? So let me write this as minus j minus omega m, okay? So the reason for this is because this omega n I could have viewed as minus omega times minus n, okay? So now I'm replacing minus n with m. So what I have here is e to the minus j minus omega times m. Okay. So if you look at this expression is the Fourier transform for x at frequency minus omega. Okay. So this is equal to x e to the minus j omega. Okay. So hence, time reversal in the discrete time has a Fourier transform that corresponds to a frequency reversal. Okay? So this is the same as in continuous time. Okay. All right. Now this last part is a little bit tricky. Right? This last part is about time expansion. Okay. So recall this is what we have in continuous time. Okay. Okay. So in continuous time, when we scale time by a, right, we're either performing a expansion or compression of the signal. Okay, so if a is greater than 1, then we're compressing the signal. And if you take a Fourier transform, this will correspond to a spectrum that is stretched out. Okay. Now, if you have a less than 1, then you're expanding the signal in time, but then in the frequency domain, you're compressing it. Okay, so you have this, opposite behavior in the time and frequency domain. Okay, but this is not directly extendable to the discrete time case, because in discrete time, this would correspond to something like this, right? X of a times n, okay? But when you do this in discrete time, you have to be very careful because this signal is defined only for integer values of this index, okay? So when you multiply n by a, giving you something that does not result in an integer, then this is not valid. Okay? Right. But we can still look at something that is, more or less related. Okay? So instead, in discrete time, we can look at something like this. Okay? So using the signal x of n, we can construct a signal we call x sub k of n, which is defined as x of n over k if n is a multiple of k and 0 otherwise. Okay? So what this does is basically expanding the discrete time signal, okay, by k times, and then inserting 0 in between. Okay? So for example, here, we're choosing the case where k is equal to 3. Okay? So we're stretching the signal by 3 times. Right? We stretch this out by 3 times, and then we insert 0 in between. Okay? Right? So now, consecutive samples now are distanced by 3 samples, and then you have 2 zeros in between. Okay. So what would be the spectrum for this stretched signal? Okay. So if you have, enough insight about this time and frequency relationship, then you should expect that when you stretch the signal in time, this should correspond to a compressed frequency domain. Okay? And let's see if that is the case. Okay. So the Fourier transform of this, okay, is the summation of the signal times e to the minus j omega n. All right? Now this signal is non-zero only for integer values of k. So you can actually change this summation from a summation over all n instead over a summation only over integer values of k. Okay? So you sum over x sub k of rk for r from minus infinity to infinity. Okay. And x sub k of rk, we can substitute with this value inside, okay, which is xr. Right, so this value is just xr. So eventually what this gives us is xr e to the minus j k omega r. And this formula here is exactly the Fourier transform of x at frequency k omega. Okay? So hence, xk n has a Fourier transform that is capital X e to the j k omega. Okay. So due to this factor k, right, the spectrum here is compressed by k times. Okay. All right. Now let's look at an example of this. So suppose we start out with this square wave for xn, right, which gives you this sink-like spectrum as we derived before. Okay? Now suppose you stretch this signal by 2. All right, so the subscript here is 2. Suppose you stretch it by 2, inserting a 0 in between. Then you can see that the spectrum here is actually compressed by 2 times, right? So originally, this peak here occurring at pi now occurs at pi over 2, right? And this peak at 2 pi now occurs at pi. Okay. Now, if you further stretch this, okay, by 3 times, then your spectrum will be compressed by 3 times. Okay? So originally, this peak at pi now occurs at pi over 3. Okay? And originally, this peak at 2 pi now would occur at 2 pi over 3. All right? Okay. So let me look at one more example before we break. Okay. So this example here is also using the property that we just showed. Okay. Now in this problem, we're asked to find the Fourier transform of a discrete time signal x that looks like this. Okay. So this xn, you can actually split into this signal plus this signal, okay? So you're taking these lower samples here and taking the larger samples here, okay? So let's call this, okay, suppose I have a signal yn that is this square wave, all right? Then this signal here is just yn stretched by 2 times. All right, so this is stretched out with a 0 inserted in between. Okay. And what this signal is actually this stretched out signal shifted, time shifted by 1, and then scaled by 2. Okay? So if you have a signal yn that looks like this, then your signal xn can be written as yn stretched by 2 times plus 2 times the stretched signal time shifted by 1. Okay? So by identifying this fact, we can then easily obtain the spectrum of x from the spectrum of y. Okay. Now, first of all, let Gn be a rectangular pulse, a rectangular signal with n1 equal to 2. Okay? So this is referring to example 5.3. Okay? So Gn is a rectangle with n1 equal to 2. So if you look back, okay? So this is example 5.3. Gn is this square signal with n1 equal to 2. Okay? Now, this signal goes from -2 to 2. All right? But if you look at yn, yn actually is not symmetric about 0, but instead it's shifted to the right by 2. Okay. So yn is actually Gn shifted by 2. Okay. So and let yn be equal to gn minus 2. Okay? So therefore, the spectrum of y is just the spectrum of g, which is sine 5 omega over 2 divided by sine omega over 2 times a phase shift, which is e to the minus j 2 omega. Okay? So this is the Fourier transform of g, and this accounts for the time shift of 2. Okay. And we know that y2n is yn stretched out by 2. So it compresses the spectrum by 2. So we have capital Y of e to the j 2 omega. Okay? And 2 times y2 of n minus 1, okay, is just 2 times y e to the j 2 omega times a phase shift. Okay? So this 2 accounts for this 2. This phase shift accounts for the time shift in the time domain. So then x, the Fourier transform of x is just this, the sum of these, the Fourier transform of these two. Okay? So hence, x e to the j omega is equal to 1 plus 2 e to the power minus j omega times e to the minus j omega sine 5 omega sine omega. Okay? So I'm summing these two. So I get 1 plus 2 times e to the minus j omega, okay, times y, and y is this, okay? So times y with 2 times omega, okay? So y is this. If you substitute omega with 2 omega, 2 cancels out here, and I should have, so I should have 4. I should actually have 4 omega here, right? Okay. All right, so that's all. So next week, we'll continue to finish up this part of chapter 5. Okay, so everything is more or less the same as in the continuous time case. So I didn't want to spend too much time on this. Okay. So we also have this differentiation in frequency. We have the Parseval's relation. And then in the next set of slides, we have the convolution property, multiplication property. So this is just repeating again for the discrete time case.